Hey, all right. So forgive me, working very quickly through my lunch here. Looks like we are about ready to get going. Oh, camera is not connected. Okay. So we can get this to play ball. There we go. All right. So welcome to our second to last MAC1147 lecture of the semester. I just want to say I'm really proud of you guys for hanging in there and getting shit done and still managing to learn, even though things have been so weird and so challenging. I'm remarkably proud of all of you, especially you guys who've been coming to these meetings every day. It's amazing. I know it's not an easy thing to do, and you've all done an exceptional job of hanging in there and staying tough and persevering through this deeply, deeply frustrating time. This is, of course, MAC 1147, section 1. On today, which is the 22nd of April. And today we're going to continue talking about summation notation, infinite series, sequences, all that good stuff. Mostly I want to give you a feel for that sigma operator. So we developed some results last time. I'll kind of remind you of the big results so far. We had a couple definitions, a sequence is an ordered list of numbers, aka a function whose domain is a subset of the natural numbers. Natural numbers, remember, are the counting numbers, 0, 1, 2, 3, 4, 5, 6, and so on. A series is the sum of the terms of a sequence. These are the two main definitions, and within sequences we talked about a bunch of different types. We have geometric sequences, probably the most important, also arithmetic sequences, and we talked about recursively defined sequences. When we talked about series, we talked about geometric series. We had a big result there. And then we also have a few littler results. So geometric series is one of the form S equals sigma n from wherever. I usually start mine at 0, a naught times r to the n, i.e. a sum of a geometric sequence. An equals a naught times r to the n. So if you build a series, sigma an, where the an's are geometric, like these guys, they look like this. And the big theorem here was, this is what we proved last time, if the absolute value of r is less than 1, then s equal to sigma n from 0 to infinity a naught r to the n converges and has value s equal to a naught times 1 over 1 minus r. So this is the most important points of the things we've talked about so far. Now remember, the infinite series is all about the sequence of partial sums. So in order to understand S, in order to prove this theorem, in order to do any work with any infinite series, you look at this series that instead of going out to infinity stops somewhere. And I usually use capital N for the place where the series stops. Your textbook unfortunately uses little n for that sometimes, which can be very confusing. Because little n and capital N don't mean the same thing. But nevertheless, I wanted to talk today a little bit more about this sigma operator. So what does that sigma thing do? How does it behave algebraically? What sort of stuff can you and can't you do with it? And I also want to develop a few results that'll be useful in Calc 1 when you talk about Riemann sums towards the end of the class there as you develop the integral. So algebra of sigma slash summation could say recall that the sum from n equals wherever 1 to capital N of any little function of n there, an, is going to look like a1 plus a2 plus a3 out to a capital N. So this summation operator, the sigma operator, is really a shorthand for this addition problem. And some examples we saw, like the sum from n equals 2 to 5 of 1 over n squared would be 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared. So you just take this thing, sorry. So the example we did there. So the sum from little n equals 2 to little n equals 5 of 1 over little n squared. This is read as the sum from n equals 2 to 5 of this thing, 1 over n squared. You compute by taking this piece right here, 1 over n squared, which is a sequence, plugging in all of these values for n, so 2, 3, 4, 5, because those are all the natural numbers between 2 and 5, and then adding them up. So that's what the capital sigma does. It takes this thing and adds up all these terms over this range of n. Hopefully at this point you guys are getting to a place where you're fairly comfortable with that notation, which means it's the right time to start talking about the algebra of that operator. So properties of sigma. If I have sigma n from wherever, I mean, it doesn't have to be from 1, it could be from j to k of some constant times my sequence an. Maybe I'll I'm going to make this a 0 just so I don't confuse things too much. Remember, this is the shorthand for C times A0 plus C times A1 plus C times A2 plus all the way out to C times A, whatever this number is, K. And if this number was something other than 0, we would just start at that number. Like if this number was 1, then we would just get this piece. Well, this is a constant multiplying every term in a sum. So I can factor that C out. And we actually did this yesterday. And here I get A0 plus A1 plus A2 plus all the way out to AK. And then finally, this last guy, I can rewrite in summation notation as C times sigma n equals 0 to k of an. So constants can pop out. That's the idea. If I have a constant inside a series, that is a piece that doesn't have any of these guys in it, whatever this index of summation is, and he's multiplying what's going on inside, then that's the same as multiplying on the outside of sigma. So for example, sigma 2 times 1 over n cubed summed from wherever 1 to 20 would be the same as 2 times the sum from 1 to 20 of 1 over n cubed, because the 2 is a constant. That's our first property, is that this is equal to this. You can write it in a single line as sigma C times an is equal to C times sigma an. And sometimes when we write about, when we talk about these properties, we like to leave off the bounds because this is really true independent of the bounds. And that's why I was like hesitating whether to write a j or a 0 or something else down there as my starting value of the sum. But if you are more comfortable leaving the bounds in, you know, you can use whatever you want here. So as I wrote it there, it would be like this. So constants can pop out of sums. The next important property is additivity. If I have the sum from 0 to k or whatever of two sequences inside there, this is, we all know it's A0 plus B0 plus A1 plus B1 plus A2 plus B2 plus all the way out to AK plus BK. Right? Because I'm taking this, whatever's in here, and I'm adding those up as k runs, or as n runs from 0 to k. But this is an addition problem, so this addition can be done in any order I want. So I could reorder this as A0, I can take the A's and put them all together, plus A1 plus A2 out to AK, and then I can do the B's separately, B0 plus B1 plus B2 plus out to BK. And each one of these on their own can be written in sigma notation. Hammy be good. Which means that this is equal to this. So in other words, the other important property of this sigma operator, the first one is that constants inside can be popped out. The second important one is that you can split the sum up over addition. Sorry, it's a habit writing infinity up there. So the sum sigma an plus bn is the same as sigma an plus sigma bn, as long as the indices match. So this would also have to run 0 to k. These two properties together make the summation operator sigma what's called a linear operator. Linear operators are your friend. In Calculus 1, the first linear operator you're going to meet is the differential operator. And then you'll construct the integral operator using sigma operators like these. And this fact that you can split them up over addition and pop out constants, very, very useful, like unbelievably useful. So I wanted to make sure I gave you those. This is a little bit of the proof and a little bit of the result mixed together. So let's give the two big properties here. Sigma c times an is the same as c times sigma an. And this is independent of the bounds, whether you're talking about finite series or infinite series. No matter where the series starts and stops, this always works. You can put some bounds in here if you want, like say from n equals 0 to k, or from n equals 0 to infinity, or from n equals j to k, whatever you want to write. But the important thing is that constants pop out, and you can split them up over addition. What is this? That's some shit stuck in here. Right. An plus sigma bn. All right, so you can split series up. Split them up over addition, you can pop out the constants. That's the big deal. That's what makes that a linear operator. One of the other things I wanted to talk about today was what you can do with the index. So this is just another example here. I would like to, so playing with summation notation. I just want to kind of give you a feel for how well this thing works. And I want it to feel concrete. So let me sum like n squared from n equals 1 to 7. I know that this is 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. I could take these first three guys and rewrite that in sigma notation. And separately from that, I could take these last four guys and write that in sigma notation. So one of the other things you can do with this sigma operator is split up over the range of the indices. This first piece is the same as the sum from 1 to 3 of n squared plus the second piece is the sum from n equals 4 to 7 of n squared. So for any k, let's say for any j between 1 and k, the sum from n equals 1 to k of an is the same as the sum from n equals 1 to j of an plus the sum from n equals j plus 1 to k of an. This is kind of one last little property here. And I thought it might be helpful for you to see this operator do some of these things before we get to the last little bits of stuff we're going to say about them. Questions on any of these properties here? I feel like we understand what each of those is saying. If you have a question, it would be a good idea to ask. This is the best time to ask. Are you comfy with what I'm doing here when I leave off the indices? I'm just saying I don't care what the indices are, right? For any indices, this shit works fine. And this property up here, this has explicitly to do with the indices, so I have to write them in order to get that to make sense. Cool. Okay. So then, I want to do a couple more examples of computing the sum of a geometric series, but I want to do some where things are not as straightforward as they were in the example we looked at last time, or the examples we looked at last time. So let's find the sum of the infinite series sigma, let's say n equals 3 to infinity of, how about 2 times negative 0.12 to the n. So this is a kind of new looking series for us. It is geometric. Here an, the things being added up, is the geometric sequence 2 times negative 0.12 to the n. This is a geometric sequence. So the series here, maybe I'll give it the name S. So S is a geometric series because it's the sum of a geometric sequence. We had that formula. That if the absolute value of r is less than 1, then the sum from 0 to infinity of a naught times r to the n would be the same by what we just showed there as the sum from 0 to infinity of r to the n with an a naught out front is the same as a naught times 1 over 1 minus r. But I can't apply this formula directly to what I'm looking at here in this problem, because in my formula, n starts at 0. Up here, n starts at 3. There are easy ways to get around this, and there are hard ways to get around this. I think the easiest way to get around this is to try and fiddle with our series until it looks like that. In other words, I'd like to do something to change that n to a 0. And I think to help you see how to do this, I'm going to write this series out. So this is all about getting comfy with the sigma notation and the sigma operations. First, I can pop out the 2. Like that. That's one of those properties that we discussed just a little bit ago here today. And now I'm just going to write it out. It's always a good idea when you're playing around with this series and you don't know what else to do. Just go ahead and write the damn thing out. So this is negative 0.12 cubed plus negative 0.12 to the 4 plus negative 0.12 to the 5 plus negative 0.12 to the 6, and so on, right? Forever and ever, amen. Do you see a common factor there? In those big parentheses, do all of those terms have any factor in common?
Negative 1.2.
Yeah, in fact, negative 0.12 cubed is common everywhere there. So I can go ahead and pull that out. So this is 2 times negative 0.12 cubed, and then this piece would become a 1. This piece would become negative 0.12 to the 1. This piece would become negative 0.12 squared. This piece would become negative 0.12 cubed, and so on. And now this series, as I have it written down here at the bottom, this piece could be rewritten in sigma notation looking like this. So this is 2 times negative 0.12 all cubed times sigma n equals 0 to infinity, negative 0.12 to the n. Because remember, 1 is negative 0.12 to the 0. That's how that showed up there. So this sort of manipulation will now allow me to use my formula. This is geometric. With r equal to negative 0.12. So the absolute value of r is positive 0.12, which is definitely less than 1. So I can use my formula. So S equals, I'll have these guys, 2 times negative 0.12 cubed times, now I use my formula, my 1 over 1 minus r formula on this. This is a naught, and 1 over 1 minus negative 0.12 would be the rest. And now the rest of this, you do a little bit of computation. This is going to be 1.12 downstairs. So you end up with 2 times negative 0.12 cubed over 1.12. I can put this in a calculator if we want, get a feel for it. It's a small number. It's a very small number. Negative 27 over 8750. If you clean it up and compute it as a fraction. But the big thing is this step, right? Being able to go from here to here and then from here to here, so you can use your formula. There is a sort of cheat code I have for this, and I'll show you that in just a second. Notice that this piece right here, the negative 0.12 cubed that ended up out front in my formula, is the same as the starting term of the original series. If you want to think of it with the 2 inside, like here, then this piece with the 2 and the negative 0.12 cubed is the starting term. So there is another way to remember that formula that I gave you at the end of class last time. The sum of a geometric series. And really, this is the better way. That if instead of a naught times 1 over 1 minus r, use this. This formula works great if your geometric series starts at n equals 0, but many geometric series that we want to play with don't, like the one we just looked at started at n equals 3. if your geometric series does not start at n equals 0, use this. So figure out what the starting term is, and then divide that by 1 minus the common ratio. If I apply that to the series we were just looking at, this has starting term 2 times negative 0.12 cubed, and then 2 times negative 0.12 to the 4, and so on. Then I take this starting term, 2 times negative 0.12 cubed, and I divide that by 1 minus the common ratio. I get the result right away. Can be a big time saver. And to me, it's even a little bit easier to remember, right? Rather than like a naught times 1 over 1 minus r, I just remember, oh, well, whatever the starting term is, divide that by 1 minus the common ratio. Cool stuff, right? Any questions on this alternate version of the formula? So then the last thing I really wanted to do with you guys regarding series sequences and series is to give you some useful results. So that result on geometric series, definitely very useful. There are several results for finite series that are also very useful. We had this one, that the sum from 1 to capital N of n, which is just 1 plus 2 plus 3 out to n minus 1, and then n, the sum of the first n positive whole numbers is n times n plus 1 all over 2. It's a useful thing to know for a lot of reasons. You can imagine a lot of different scenarios where you need to add up the first 50 or 20 or 75 positive numbers. You got a nice formula for it. We actually proved this, right? This was the baby Gauss story where Gauss paired off the n and the 1, and the 2 and the n minus 1, and the 3 and the n minus 2, and observed that he had n over 2 copies of n plus 1. There are two other things like this that you will use at the right around the 2/3 point in Calc 2, in Calc 1, as you're getting ready to develop the integral. That's the sum of squares and the sum of cubes. This guy is, of course, 1 squared plus 2 squared plus 3 squared out to n minus 1 squared, and then n squared. And he turns out to be related to this guy. He's n times n plus 1 times 2n plus 1 all over 6. I've seen a geometric argument that tries to explain this. There isn't one that I'm like particularly fond of, at least not that I know well. But I am aware of one. Oh, not cubes, some squares. Forgive me for just 1 second while I'm looking here. Yeah, here, I'll show you. This is it. So here's the sum of the first n positive integers, and this is just a little proof, same as the proof that we went over last time, where you pair up n and 1, 2 and n minus 1, 3 and n minus 2, and you get a bunch of copies of n plus 1. They work some examples. They do the sum of odd integers, but where's the sum of squares? So sum of squares, the first n positive integers. Yeah. So, this is not a nice proof. Yeah, so none of the proofs that I found of these are super intuitive. I do wish I had a nice one for you. The way I usually prove this when I need to, oh, here we go. The way I usually prove this when I need to is by mathematical induction, but that's not something we have handy. Yeah, no, these are all using heavier duty stuff. That's the same as the last one. This one promised to explain it visually. Sum of the first n squares, so maybe you can follow. So they're going to take each of these blocks and say that each of these blocks has volume 1. So here is 4 blocks, so this has volume 4, which is 2 squared. Here is 9 blocks, so this has volume 9, which is 3 squared. So I'm going to take these blocks and arrange them into squares. And then they're going to stack the blocks. They generate 3 more of these things, exactly the same. I'm going to put them together. That dimension is n, the height here. That's cute. So they slice that top row. I don't know if you guys caught that. What they happened there is very clever. They take this top row and they slice all of them in half. And those then distribute nicely over the top. So you end up with a height here. This chops off at n, and then that last little half block there is of height 1/2. So the dimensions are n times n plus 1 times n plus 1/2. Very clever.
Trippy.
It is, yeah. And there's lots of great YouTube videos out there like that. If you're ever having trouble understanding a concept or the origin of a formula, just Google around until you find something that appeals to you. It's a great strategy. From here, things are very, very easy. They just combine algebraically and you get the result. Yeah, not exciting from here. So that's it. That's the formula. The alternate approach is to prove by induction. And induction is something that you will want to get good at if you intend on going forwards in proof-based mathematics. But for our purposes here in pre-calculus and for the purposes of calculus itself, induction is not really that important. The last formula that you will be using somewhat frequently at that middle part of Calc 1 is the sum of the first n cubes. And this is also a cool result, right? Of course, this is 1 cubed plus 2 cubed plus 3 cubed, and so on. Second to last term is n minus 1 cubed, and the last term is n cubed. This turns out to be a perfect square all the time. Not only that, it's the square of this. It's the square of this, which is surprising. It's n times n plus 1 over 2 all squared. I do not know, again, similar to the last one, off the top of my head, an argument besides an inductive argument to prove this. But I'm sure if we Googled around a little bit, we could find some similarly cute video. Oh no, induction. Maybe not. This one might be a little bit tougher to get the result on. But really, that's it. That is it. So maybe for our last couple little examples here today, I'll make use of some of these formulas. But then we are done with all the material we need to talk about in this section. So I'll leave it up to you guys. We got two options for the rest of class today. I could use these formulas a couple times to find some numbers for you, like the sum of the first 20 cubes or the sum of the first 15 squares. Or I could show you the binomial theorem, which is another kind of interesting series formula. So any preferences there between examples of these things or the binomial theorem?
We do a homework number, the homework number 22.
Sure. Yeah, let me pop that up. All right. Yeah. So there they're asking you for the partial sum of a geometric series. Let's take a look. So we're asked to find, and your numbers might be a little bit different than mine.
Also, I have another quick question. Did the variables matter? Or like whenever they use K or I or N, does that make a difference?
Nope.
Okay.
As long as the pieces that go in the one spot are, as long as everything's going in the right spot, you know, you're taking the piece from here and using it where you should in the formula and so on. It doesn't matter what symbol you use for the index of summation. So they're using a K here. We've used N's most of the time.
There was an I in the homework, and it threw me off because of the imaginary numbers.
So sometimes I is used as an index of summation, but no, that's not related to the imaginary unit. So for whatever reason, the numbers that we like to use for indices are like I, J, K, L, M, N. And it's unfortunate that there's that overlap there with I being the imaginary unit also. But yeah, no, not intended to be like that. So here what we want to do is remember our formula for the partial sum of a geometric series. So I would say recall that the sum from, I'll write it in terms of K equals 0 to capital N of R to the K is 1 minus R to the capital N plus 1 over 1 minus R. All right, this was our formula for the partial sum of a geometric series starting at 0. Everybody remember this? This is the thing that we were able to pull out by multiplying both sides by 1 minus R and then kind of simplifying and then dividing the 1 minus R back over. The formula for the partial sum of a geometric series. Now there's some differences between what our formula looks like and what this looks like. First, there's that 5, but he's not a problem because we know constants can come out. So then what's left is the sum K equals 1 to 4, negative 2 to the K minus 1. Honestly, this sum is so small, I might be inclined to not even use this formula. I might be inclined to just write the thing out. But let's do it both ways. I think it'll probably be faster here to write the thing out. So we can use this. But we don't need to. So this guy is the same as 5 times, I'll open up a big parentheses, negative 2 to the 1 minus 1 plus negative 2 to the 2 minus 1 plus negative 2 to the 3 minus 1 plus negative 2 to the 4 minus 1. Yeah, this sum is so short that we don't even need that formula. But this is the same as 5 times negative 2 to the 0 plus negative 2 to the 1 plus negative 2 squared plus negative 2 cubed. So that's 5 times 1 minus 2 plus 4 minus 8. And you can do this addition, subtraction, whatever order you want. I would say maybe that's the same as 5 times 1 minus 2 is minus 1, and 4 minus 8 is minus 4. So that's 5 times negative 5, or negative 25. Right, so this is the approach that feels most natural to me for this particular problem because that sum is so short. But if this series ended at 400 rather than at 4, I would not want to do it this way, right? That would take far too long. So how could I have made use of that formula? It's going to be a similar thing to what we were doing with our other slightly different geometric series. First, any questions on what we did here, how we were able to get that answer like this? Okay, let's see how to use the formula. In some senses, that's more fun. If I come back to this line, this is 5. I'm going to call the thing S, so I have a name for it. So S is equal to 5 times negative 2 to the 0 plus negative 2 to the 1 plus negative 2 squared plus negative 2 to the 3, which I can rewrite in sigma notation as 5 times sigma k equals 0 to 3 negative 2 to the k. So I'm able to get rid of the k minus 1, and I'm also able to rewrite my series as a series whose starting index is 0, which puts me in good shape to use that formula. So the formula in my recall box here, I could then break him out, just bringing the 5 along for the ride. According to this formula, the sum from k equals 0 to 3 of negative 2 to the k should be 1 minus negative 2 raised to the 3 plus 1 is 4 over 1 minus negative 2. Now, that's the same as 5 times negative 2 to the 4. What is that? 16, right? So that's 1 minus 16 divided, but down here now I've got 1 minus negative 2. That's 1 plus 2. That's 3. So altogether, this is 5 times negative 15 over 3, which is 5 times negative 5, which is, again, 25. negative 25. So two different approaches. If the series went from k equals 1 to 400 or 40,000, I would definitely want to do it like this, right? Because I don't want to write out the full sum from 1 to 40 or 400,000. That would take too long. But since this sum was small enough, we could have just computed it barehanded like this. Nothing wrong with that. So either approach here is just fine. Questions on either of those methods? I think this is really cool shit. The first few times I saw this and started playing around with it, it blew my mind all to pieces. I remember just being kind of dumbfounded that these formulas worked and wondering where they came from and how people knew to discover them. And those videos, like that little video I showed you, opened a whole new world for me. It's really, really magical stuff. And the good news is that finding formulas like that is a very rewarding part of research mathematics. Summing infinite series or even summing some finite series. Valuable, meaningful work that you can often find clever ways to approach. I think we might have time for one or two more from the homework if there's anything like that that you guys would like to look at. Yeah, we still got about 20 minutes. If there isn't anything else in the homework that you guys particularly want to look at, then I would like to show you the binomial theorem. This is a nice payoff for learning sigma notation. Do you ever get tired? Not like in general, but do you ever get tired of multiplying out stuff like 1 plus x to the 10 or x plus 3 to the 7? If you have to multiply something like this out, it's a real chore. Now you got to FOIL, right? But it's not like just a square. You got to FOIL like 10 times or 7 times. You have to keep multiplying out, multiplying out, multiplying out. It takes forever. Turns out there are nice formulas for this. For things like 1 plus x to the capital N, and even things like x plus y to the capital N. Those things are binomials, right? 1 plus x or x plus y, those are binomials. And when you want to raise a binomial to a large power, you can use what's called the binomial theorem. It involves a little bit of notation. So first I'll show you the formula. This is the sum from little n equals 0 to big N of big N choose little n times x to the little n. And I'll show you what this weird parentheses thing means here in just a second. But of course, if I was writing this out, this is big N choose 0 times x to the 0 plus big N choose 1 times x to the 1 plus big N choose 2 times x to the 2 plus, and then we end up at big N choose big N times x to the big N. So if you know what those parentheses numbers are, then you can expand anything that looks like this very, very quickly. The other formula looks like this. Very similar looking. In fact, the formula above is just this with y plugged in as 1. It's that. And in each of these, the binomial coefficients, they're called, this is n times capital N times capital N minus 1 times capital N minus 2, all the way down to capital N minus, what is it, little n, I think about this, little n plus 1, little n minus 1. Yeah, little n minus 1 over little n times little n minus 1 times little n minus 2 all the way down to 3 times 2 times 1. This is actually, sorry, this should be a plus 1. Yeah. It can be written in terms of the factorial notation as capital N factorial over little n factorial times capital N minus little n factorial. And the factorial of a number is just the product of that number and all of the natural numbers less than or equal to him. So this binomial theorem business can be nice, can be a useful way to expand large powers of binomials. And there is a fast way to remember what these binomial coefficients are that doesn't require using these formulas. So I'll go ahead and show you that. That's called Pascal's triangle. And then we'll use that formula to expand a couple things. Pascal's triangle is a mnemonic. I'm probably misspelling that. For remembering binomial coefficients. So it's a triangle. At the top you put a 1, and then right down here you put 2 more 1s. And then to generate the next row, you always start with a 1, and then you add the 2 above to get the guy below. So I have 1 plus 1 here is 2, and then the row always ends with a 1. My next row starts with a 1, and then I add these 2, that's 3. And then I add these 2, that's 3, and then I end with a 1. And then my next row looks like 1 on the end, and then 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then I end with a 1. And so on. So I could build as many rows of this triangle as I wanted to. The way this relates to the binomial coefficients, this top row is like row 0, this is row 1, this is row 2, this is row 3, this is row 4. The way this relates to the binomial coefficients is like this, x plus y to the 0, that's just 1. That's coming from row 0. X plus y to the 1, I know, is 1 choose 1, so the binomial coefficient with 1 and 1, x, plus the binomial coefficient 1 and 1 of y. And both of these numbers come from row 1, so this is 1x plus 1y. And of course, we know that, right? We know x plus y to the 1 is just x plus y. X plus y squared is 2 choose 1 times x squared plus 2, the binomial coefficient with 2 and 2, x, y, plus the binomial coefficient 2, oh, sorry, this should be 2, 0, 2, 1, and then 2, 2 of y squared. And each of these numbers comes from this, from row 2. So this is 1, 2, 1, 1, 2, 1. So this is 1x squared plus 2x y plus 1x squared. X plus y cubed would similarly be 1x cubed plus, what's the next guy here? 3. So 3x squared y plus 3xy squared plus 1 y cubed. And x plus y to the 4, it's going to follow these same patterns where the powers of x go down, the powers of y come up, and I have these coefficients. So I'll start out with 1x to the 4, and then I'll have 4x cubed y, because this is a 4, and then I'll have plus 6x squared y squared, because this is a 6, and then I'll have 4xy cubed. So notice the power of x comes down by 1 each time, and the power of y comes up by 1 each time. And then my very last guy here, this would be another 1, x to the 0 times y to the 4. So this can give a fast way to expand binomials. It's a little bit silly, and it's not directly related to any of the things we've been doing, but I wanted to show it to you because it's just one of those neat things. Holy crap. Sorry, got a weird text there. So if there aren't any more particular questions from the homework, then this is where I intended to stop the lesson for today. Is there anything else that's been bugging you guys in the homework that you would like to talk about, or anything like that?
Number 11.
Yeah, let's take a look. So here they give us a recursive sequence, and they ask us to find the first 5 terms. And they tell us that A1, the initial condition, A1 is 1, and that in general, AN is equal to 2 times AN minus 1 plus 7, like this. So they want A1, A2, A3, A4, and A5. A1 they already told me. A1 is 1. A2, according to the recurrence relation, should be 2 times A1 plus 7.
Can't see your screen.
Oh, shit, sorry. There we go. So here's the recurrence relation. This tells me how to get the next guy from the previous guy. To get the next guy, I multiply the previous guy by 2 and then add 7. A1, they told me, is just 1. So the first thing they asked me for, A1 is 1. A2, I then have to compute from A1. So A2, according to this recurrence relation, is 2 times A1 plus 7. So in other words, I'm plugging n equals 2 here. I'm plugging n equals 2 into this recurrence relation, and that tells me A2 is equal to 2 times A sub 2 minus 1. That's A1 plus 7. And A1 is 1, so this is 2 times 1 plus 7, which is 9. If I plug n equals 3 into my recurrence relation, I get A3 equals 2 times A3 minus 1 is A2 plus 7. And A2 is 9, so this is 2 times 9 plus 7. 2 times 9 is 18, and if I add 7 to 18, I get 25. Make sense so far?
Yes.
Okay, so we'll keep going. If I look at n equals 4, according to my recurrence relation, a4 should be 2 times a3 plus 7. So that's 2 times 25 plus 7. 2 times 25 is 50, so that is 57. And when I look at n equals 5, a5 is 2 times a4 plus 7, which is 2 times 57 plus 7. I got to think about that for a minute. 2 times 57 is 114, plus 7 is 121. Getting some interesting numbers out of this, right? Getting a lot of squares out of this, but not all squares. But that would be it. Those would be the first 5 terms of this sequence: 1, 9, 25, 57, and 121. And the trick is to just use the recurrence relation. So in order to get the next guy, you have to know the previous guy. I couldn't find a6 without knowing a5, because all this tells me is that a6 is 2 times a5 plus 7. But if you have the previous term, you can get the next term. And the way to do it is just multiply the previous term by 2 and then add 7. That's what this guy is telling us. Okay.
Got it.
Cool. Alrighty, so that's where I'm going to go ahead and end the meeting for today. Continue working on this sequences and series homework. And after class next time, I will give you the take-home exam, which you guys will work on for exam 4. And that will be due on the day of the final. We'll talk a little bit more about the final. Having finished playing around with Honor Lock, I have a fairly good feel for it, and I would like to use it to proctor our final. I think it does a little bit of a better job than WebAssign, and it gives me some stuff to go over if I were to ever need to review something. So the test will still be on WebAssign, but we'll access it a little bit differently than we did last time, because we're going to use the Honor Lock proctoring Chrome extension. But I will talk about that at the end of class next time, and then I'll hand out the take-home for exam 4, and you guys will be done with MAC1147. So, you know, bravo.
Will you be doing office hours next week as well?
I
The same Tuesday and Thursday?
Yep. Yeah.
Okay.
Yeah. Need to get a hold of me, or if you've been like sitting in the waiting room for the office hour forever and I haven't gotten to you, send me an email or a Canvas message. I know that does happen sometimes. I get a little busy or distracted. But yeah, yep, same office hours next week, all through finals.
Hello, sir.
Is there a question?
Hello.
Hi.
Yeah, can I see the paper where you note Pascal triangle?
Yeah. Oh, maybe. There it is.
Okay, okay, let me take a picture of it.
Sure, yeah.
Can you push it a little bit?
Mm-hmm.
Okay, got it, thank you.
Sure, of course.
Okay, got it, thank you.
Great, yeah, no problem.
Okay, bye.
Bye. Right, I'm gonna go ahead and stop the recording here then, and I will see you guys tomorrow afternoon.
Thank you.
Thank you.